Ever watch a rocket launch and wonder, how do they, like, calculate its trajectory? I mean, with pinpoint accuracy.
Yeah.
Or maybe you've seen a perfectly executed stunt in a movie, and you're just like, how did they figure that out?
Right.
Well, get ready to unpack the math behind all those incredible feats.
Okay.
It all comes down to kinematics
Uh-huh.
and the magic of calculus.
Absolutely. It's all about motion. How things move, why they move, the mathematical laws that govern all that movement in calculus. Well, calculus gives us the tools to analyze these movements in some really incredible ways.
So where do we even begin? What are the basic building blocks of motion that we need to get a handle on?
Okay, so everything starts with the frame of reference. Imagine you're trying to give someone directions.
Okay.
But you don't have any landmarks, no street names, nothing like that. It would be impossible. We always need a point of reference to describe motion. And that's where coordinate systems come in. Think about your X, Y, and Z axes. Classic, right? Those give us a framework to pinpoint an object's position in space.
So if I say a car is 10 meters to the right of our starting point,
Right.
that starting point, that's my reference frame.
Exactly. And from there, we can start talking about distance and displacement. These two often get confused, but they're distinct concepts. Distance, that's simply the total path an object travels.
Gotcha.
Displacement, on the other hand, is the overall change in position from start to finish.
Okay.
Considering both how far it moved and in what direction.
Oh, okay, so if I walk a full lap around a circular track, I might cover a significant distance.
Right.
But since I end up right back where I started, my displacement would be 0.
Exactly. It's a great example of how distance and displacement can differ, and it highlights another key concept, distance. That's a scalar quantity. It only has magnitude. Displacement. Displacement is a vector quantity because it has both magnitude and direction.
So a vector's like an arrow. Its length tells you the magnitude, like how far.
Yes.
And the direction that it's pointing tells you the direction.
Exactly.
Okay, that makes total sense for displacement. But where do speed and velocity fit into all of this?
Okay, so speed and velocity are all about how quickly an object changes its position. Speed is simply the rate at which distance is covered. Always a positive value. Velocity, however, is a vector. It's the rate of change of displacement with respect to time, considering both speed and direction.
So I can drive at a constant speed of 60 miles per hour?
Yep.
But my velocity is constantly changing if I'm going around a curve because my direction is changing.
Exactly. You can have constant speed but changing velocity.
Whoa.
Yeah. That's a mind bender for a lot of people.
Yeah. I'm starting to see how these pieces all kind of fit together. But where does calculus enter the picture? I vaguely remember something about derivatives.
That's right. Calculus lets us break down motion into tiny, almost infinitesimal increments.
Okay.
Let's say you glance at your speedometer. That's your instantaneous speed, your speed at that precise moment. In calculus terms, that instantaneous speed is the derivative of the distance function with respect to time.
Okay, I'm vaguely remembering derivatives from calculus class. It's like zooming in on a curve on a graph until it looks like a straight line.
Yeah.
And the slope of that line at a specific point, that's the derivative, telling us the rate of change at that exact moment.
You got it. And we can apply that same logic to velocity. Instantaneous velocity, the velocity at a single point in time. It's the derivative of the displacement function with respect to time.
So if I had a graph of an object's position versus time,
right,
I could find its velocity at any given point by finding the slope of the tangent line to the curve at that point.
Precisely. And the steeper the slope, the greater the instantaneous velocity at that moment. Now, what about when velocity itself changes? That brings us to acceleration.
Right, because things don't always move at a constant speed. Sometimes they speed up, sometimes they slow down, sometimes they change direction.
Exactly. Acceleration is the rate of change of velocity with respect to time. Like velocity, it's also a vector quantity. It has both magnitude and direction. You can accelerate by changing your speed, your direction, or both.
So if I slam on the brakes in my car, I'm accelerating, even though I'm slowing down.
You are indeed. Your velocity is changing. And any change in velocity, whether it's speeding up, slowing down, or changing direction, means acceleration is at play. And just like with velocity, we can find that instantaneous acceleration at a specific point in time using calculus. It's the derivative of the velocity function with respect to time.
Wow, calculus really is like a high-powered lens, allowing us to zoom in on any point in an object's motion and understand exactly what's happening with its speed, its direction, and its acceleration.
That's a great way to put it. Calculus gives us the tools to analyze motion with incredible precision and detail. It's not just about, like, finding those instantaneous values.
Right.
Calculus also lets us work backward from acceleration to figure out the velocity and displacement.
Okay, now you've really piqued my curiosity. How do we do that?
Okay, so remember how we used derivatives to break things down into these tiny increments?
Yeah.
Well, integration, it's like a rewind button. It lets us put those pieces back together to see the bigger picture.
Okay.
So if we know how an object's acceleration is changing over time, we can use integration to figure out its velocity over that same period.
So imagine you're, like, tracking a car's acceleration as it speeds up to merge onto a highway.
Right.
By integrating the acceleration function, you could reconstruct the car's velocity at each moment during that acceleration phase.
Exactly.
That's amazing. It's like we're reconstructing the entire motion sequence just based on the acceleration.
Exactly. And we can even take it a step further.
Okay.
By integrating the velocity function, we can find the object's displacement over time.
So by working our way backwards through integration, we can go from acceleration to velocity and then from velocity to displacement.
You got it.
Yeah.
Calculus provides this powerful framework for connecting these core concepts of motion.
Okay. Let's see if I can wrap my head around this. Let's say we have, like, an object that's moving along a straight line.
Right.
And we know its acceleration is constant at 2 meters per second squared.
Okay.
How could we use integration to find its velocity and displacement?
That's a great example. So since the acceleration is constant, we can integrate it to find the velocity function. The integral of 2 with respect to time is 2t plus c, where c is the constant of integration.
Wait, what's this constant of integration? Why does it pop up?
That's a great question. When we integrate, we're finding a family of functions that all have the same derivative. That plus c represents like a whole range of possible vertical shifts of the function. To find the specific function that we need some additional information.
Okay, so it's like we have a puzzle piece,
Right.
but we need another piece to fit it perfectly into the bigger picture.
Exactly. In this case, we might know the object's initial velocity. For instance, let's say the object starts from rest, meaning its initial velocity is 0. That means when time is 0, velocity is also 0.
So we can plug in those values, t equals 0 and v equals 0, into our velocity equation, 2t plus c.
Exactly.
That would give us 0 equals 2 times 0 plus c, which means c must also be 0.
Yes.
So our complete velocity equation is v equals 2t.
Perfect. You've just used the initial condition to find the specific velocity function that describes our object's motion.
Okay.
And now we can integrate this velocity function to find the displacement.
Okay, so the integral of 2t with respect to time is t squared plus c.
Right.
Here comes that constant of integration again.
Right. Again. So to find that specific value of c for our displacement function, we need another piece of information about the object's starting position.
Let's say the object starts at a position of 5 meters. That means when t equals 0, x equals 5.
Great. Let's plug those values into our displacement equation. 5 equals 0 squared plus c. So in this case, c is 5. That means our complete displacement equation is x equals t squared plus 5.
So we started with just the acceleration, a constant 2 meters per second squared.
Right.
And using integration and a couple of initial conditions, we've uncovered the object's velocity and displacement functions. Pretty impressive.
It highlights how calculus gives us this really powerful set of tools for understanding motion. We can break down motion into tiny moments with derivatives and then piece it all back together with integrals.
This is all starting to feel a lot less abstract and a lot more like something I could actually use to analyze real-world motion.
Exactly. And speaking of the real world, remember that rocket launch we talked about earlier?
Yeah.
The calculations involved in determining its trajectory are incredibly complex, but they all stem from these fundamental principles of kinematics and calculus.
That makes sense. So are we ready to tackle some even more challenging examples? What happens when objects aren't just moving back and forth along a straight line, but are moving in multiple directions?
Ah, you're talking about multidimensional motion, which is even more fascinating. Get ready to explore how these same concepts apply, but with an added layer of complexity and intrigue.
Okay, multidimensional motion. This sounds like we're stepping things up a notch. I'm ready for the challenge.
It's definitely a leap forward, but trust me, it's worth it. Think about some everyday examples, like a basketball arcing towards the hoop or a car navigating a winding road. These motions aren't confined to a single straight line. They involve movement in multiple directions simultaneously.
So how do we even begin to describe these more complex motions? It feels like we need a whole new set of tools.
You're absolutely right. We need a way to represent both magnitude and direction, and that's where vectors become indispensable.
Right, vectors. We touched on them briefly earlier, but I'm ready to dive deeper. So a vector, it's basically an arrow that represents both how far something moves and in what direction.
Exactly. Think of it like this. Imagine you're giving directions to a friend.
Okay.
You wouldn't just say walk 5 blocks. You'd say walk 5 blocks north. That north is crucial because it specifies the direction. A vector captures both pieces of information, the magnitude, like your 5 blocks, and the direction, north.
Okay, that makes sense. But how do we actually use vectors to describe motion in multiple dimensions?
Okay, let's take that basketball example you mentioned. As the ball flies through the air, it's moving both horizontally and vertically at the same time. We can represent its velocity using two separate vectors, a horizontal velocity vector and a vertical velocity vector.
So we're breaking down the ball's overall velocity into its horizontal and vertical components.
Yes.
Each represented by a vector.
Precisely. And this allows us to analyze the motion in each direction separately. In the horizontal direction, if we ignore air resistance, the ball's velocity is pretty much constant.
Okay.
But in the vertical direction, gravity is acting on the ball, causing it to slow down as it rises and speed up as it falls.
So even though the ball is following a curved path,
Right.
we can analyze its horizontal motion and its vertical motion as two separate, simpler problems.
You got it. It's like solving two one-dimensional motion problems simultaneously.
Yeah.
And by combining the results, we can get a complete picture of the ball's overall motion.
This is starting to click. So we can use vectors to represent velocity. But what about acceleration in multidimensional motion?
Acceleration in multiple dimensions works the same way. We can break down the acceleration into its component vectors. For that basketball, the only acceleration acting on it is gravity, which acts straight downwards.
Okay.
So its acceleration vector would point downwards with a magnitude of approximately 9.8 meters per second squared.
I see. So just like with velocity, we can analyze the acceleration in each direction separately using vectors.
Exactly. And here's the really cool part.
Okay.
Even though we're dealing with motion in 2 or even 3 dimensions,
Right.
the same equations of motion we use for one-dimensional motion still apply.
Really?
We just have to apply them separately to each component of the motion.
Wait, really? So all that calculus we learned earlier, derivatives and integrals, can still be used to analyze multidimensional motion.
Absolutely. We just have to remember that we're now dealing with vectors.
Okay.
So when we take derivatives, or integrals, we're doing them separately for each component of the vector.
This is mind-blowing. It feels like we've unlocked a whole new level of understanding about motion.
It's definitely a powerful realization. By combining vectors and calculus, we have the tools to analyze and predict the motion of objects in the real world, no matter how complex their paths might be.
This deep dive has been incredible. I'm looking at the world around me in a whole new way, seeing the vectors and the calculus at play in every moving object.
And that's the beauty of physics. It helps us understand the hidden language of the universe, the fundamental principles that govern everything, from the smallest particles to the largest celestial bodies.
Well, I'm definitely feeling a lot more physics literate now. Thanks for guiding me through this fascinating exploration of motion, from the basics to the complexities of multidimensional movement.
My pleasure. And remember, the journey of discovery never truly ends. There's always more to explore in the world of physics and beyond. So stay curious and keep asking questions.
You can count on that. And for all you listeners out there, keep those brains engaged, because there's always something new and exciting to learn about the world around us. Until next time, keep exploring.